All right, so now that we know how to find the equation of a line out in R3, we want to be able to do the same thing for planes and not just planes that are parallel to one of the coordinate axes. All right, so here I've got a plane, and this is the plane that I'm interested in finding a way to describe. And we want to think about what's the bare amount of information I would need to give you about this plane so that you could go out in R3 and find this particular plane. All right, so for a line, you just needed a point and then a direction vector, or you needed 2 points, right? So we could take the point and then we could find the direction vector that goes between them. All right, so, but it's gonna turn out that 2 points is not quite enough for a plane, right? So if I think about that line through PQ, so I could take this plane and kind of spin it around that line PQ like an axis and rotate it around, and I could find an infinite number of planes that would go through both points P and Q. All right, so I need to give you another point. If you think about this, if I tell you it also has to go through R, when I try to grab the plane and rotate it about that PQ axis, I can't do it because I'm locked into that third point P. Okay, so I at least have to give you 3 points. And you can kind of imagine if you hold your three fingers up, there's only one plane that can land right on top of those 3 points in a specific way. All right, so I could give you 3 points. Kind of as corollaries to this, I could give you that line that goes through PQ and R for the same reasons, right? It can't rotate around that axis because R is holding the plane in place. And also, I could instead also just give you the line that goes through P and R, right? If I give you these two lines out in space, there's only going to be one plane that's going to go through both of those lines at the same time. Okay, so I've just described 3 ways that I could give you information to locate a particular plane. I could give you the 3 points, I could give you a line and a point, or I could give you 2 lines. All right, so those are all good ways to describe a plane. There's actually a fourth pile of information that I could give you that would specifically describe this particular plane. It's not as intuitive as the first three, but it's actually the pile of information that's going to give us the equation of the plane. So let me turn off these 2 lines, and I'm going to turn point P back on. All right, so I'm still going to have to give you a point on the plane, but I'm also going to give you this vector n. All right, and that vector n is one of the many vectors that meets this plane at a 90-degree angle. So you could imagine one going more towards the origin, or a longer or shorter vector. So there's lots of vectors that are going to meet this plane at 90 degrees. All right, we call this vector n. It stands for normal. In Calc 3, we keep coming up with fresh words to describe a 90-degree relationship, but we're just kind of stuck with all of them. So we have perpendicular when we're talking about two lines that meet at 90 degrees, orthogonal when we're talking about two vectors meeting each other at 90 degrees. When you start meeting a plane or a three-dimensional surface at a 90-degree angle, we use the word normal. Okay, so this vector is normal to the plane. So I'm going to give you a point and a normal vector. And it turns out that there is only one plane that can pass through that point P with that normal vector, and it's this plane. All right, so why would that be? So I'm going to turn on a generic point S in the plane. We can see that that plane goes through that point S, and I'm going to let that point S kind of roam about the plane. Okay, so this point S is going to bounce around and find all of the points that lie in this purple plane. All right, so how is GeoGebra finding all the points that lie in this plane? So I've told GeoGebra to find me, oh, it went off there. So it's going off into infinity. I'll be back in a minute. I told GeoGebra to find me all the points S so that when you connect P and S with a vector, so that vector there, so find me all the points S so that when you make this vector PS, PS is orthogonal to N. Okay, so it's finding me all those vectors no matter how long they are, what direction they're pointing. And eventually GeoGebra is going to trace out this entire plane just by looking for these orthogonal vectors. Right? And this is the bit of information, that point P and that normal vector that's going to completely define this plane. All right, so we had 4 different ways we could describe a plane. We said we could give you 3 points, and the plane would go through those 3 points. I could give you a line in the plane and a point, and that would lock the plane into place. We could give you 2 lines, and the plane would go through those 2 lines. Or the last one, you could have a point in the plane and a vector normal to the plane. And I said that this is the one that's actually going to give us the equation of a plane. Okay, so here's my sorry representation of a 3-dimensional plane on my paper. And I said you were going to have a point be given to you. So let's put point P on this plane. And P we're going to say is the point x naught, comma, y naught, comma, z naught, like we did for our lines. And I also said I was going to give you this normal vector. Okay, so let's imagine that this is coming out. This normal vector is meeting the plane at 90 degrees. Okay, so that's our normal vector. And we'll use letters A, B, C, kind of like we did for a direction vector for lines. Okay, so then I said that this was going to give you all these points out in the plane S. So let me draw this generic point S in the plane. Right, and S is our generic point. So it's going to be X, comma, Y, comma, Z. And it was going to be all of the points that I could connect a vector with P so that PS was going to be orthogonal to our normal vector. Okay, so S is going to be all the points so that PS is orthogonal to N. So what do we know about orthogonal vectors? We know that their dot product is 0. Okay, so we know that if PS is orthogonal to N, that if I dot those two vectors, I'm going to get 0. All right, so let's write PS in component form. We know how to find component form for a vector. All right, so P and S up here, I'm just going to subtract coordinate-wise. So X minus X naught, S minus P. So Y minus Y naught, and Z minus Z naught. And if I dot that with vector A, B, C, the answer has to be 0. So let's actually compute that dot product. Okay, so remember dot products, we multiply X components, we multiply Y components, and we multiply Z components, and then we add them together. Okay, so this is going to be red stuff, A times X minus X naught, plus blue stuff, B times Y minus Y naught, plus green stuff, C times Z minus Z naught is equal to 0. All right, so there's your punchline. This is the equation of a plane that passes through a specific point with a particular normal vector. And in the next video, we'll use this to find equations of a couple of particular planes.